We was dealing with the first lecture. So what's the voltage source do for us?
What is the what?
The voltage source. Well, what does it do? Hey, the voltage source does the same thing, you know. Huh?
Pretty much
Yeah, but the actual voltage source does one thing in life. The push. It don't provide it makes what's there flow. Y'all understand voltage sources don't produce electrons. It takes the electrons that's already there and makes them do what? Move. It's just like a pump does not make water. What does a pump do? It takes the water that's already there and creates a difference in potential. Most pumps create vacuums, by the way, and then atmospheric pressure is actually what provides the push, believe that or not. So what the pump does and what a compressor does, or whatever you want to call it, provides a difference in potential, which causes things to move. So basically, a voltage source is the pump of electricity. It don't create electrons. All it does is what? Push the ones that's already there, that's in the material that we're working with. Okay, we talked about shorts, we talked about open, or sorry, okay there. We talked about short circuits and open circuits. You got any questions there? We talked about what the function of insulators are. So this is cable splicing. And basically, let me turn on that projector. That would help. Let me hook it up first. That would help even more.
electricity follow the path.
Well, electricity is made up of several things. So we don't usually, in the trade, or you hear people or novice in the field use the term electricity, but electricity consists of a lot of things, right? So we talk about current. So we can't say most of the current follows the path of less resistance. So if you have no resistance, then all the current follows that path. If you have a little resistance and a big resistance, then most of the current flows through the little resistance, unless the resistance are in series with each other. If the resistance are in series with each other, then the current flow is the flow of the circuit, right? You understand? If they're parallel, then the current is going to take the path of it. Most of the current is going to take the path of the least resistance. That makes sense. So we can't say the current takes the path of the least resistance, because if I've got a 100 ohm resistor and a 1K resistor across a voltage source, there's current flow through the 1K and there's current flow through the 100 ohm, but the 100 ohm has the most current relative to the 1K. Does that make sense? So if we say we have no resistance, which basically doesn't exist in life, but we can have extremely low resistance, then 99.99999% of the current would go through there, but there's still going to be some current flow through them. Does that answer your question, or did I talk around it? So in this circuit right here, oops, Still didn't turn on the projector. That would be already good. So this is a parallel circuit. So I've got a 2 ohm resistor, 5 ohm resistor, 50 ohm resistor, and a mega ohm. There's current flow through all those resistors. So we can't say current takes the path of the least resistance, right? You understand? So if this was, 10 volts, then this right here would get 5 amps. And this right here would get 2 amps. This right here would get 200 milliamps. And this right here would get probably microamps or even nanoamps. So this might be 10 nanoamps. But they all have current flow. So we can't say current takes the path of least resistance, right? You understand? Because if I've got, most of the current takes the path of least resistance. Now if I come over here and do this, now this guy's got 0 ohms. So now all 99.99999% of the current is going through that because there is really no such thing as 0 ohm, right? You understand? But it's going to be extremely low where we can't measure that. So that's why conductors are rated in ohms per 1,000 feet. So if we look at a 24 gauge wire, it says like 30 ohms per 1,000 feet. Right? You understand that? So how much would it have for 1 foot? Well, our instruments wouldn't be able to measure that. So if I put that wire across something, then that means the current flow through that is going to be extremely large. And I hate people that says current takes the path of least resistance. Because you get in your mind what? But you've heard it from somebody else. You just didn't make that up. And I've heard instructors say that current takes the path of least resistance. I've heard instructors take that. And what do you think right off the bat? Well, what you think right off the bat is all the current takes the path of least resistance, and that's not true. In a series circuit, the current is the same through the circuit, so you can't say current takes the path of least resistance when the current flow is the same throughout the circuit, right? You understand? Well, there's it's relative to the current. So current take, the majority of the current takes the path of least resistance. Good morning. Morning. I have no idea. She's not in this office.
Okay, I'll give her a buzz quick.
You got her office is actually over in this side.
Okay, thank you.
So that's why if we have a short circuit, then 99.99999% of the current is going to go through the short. Okay, so we looked at the symbols, we looked at the different types of diagrams where conductors are used at. We talked about voltage, amps, and resistance. Then we talked about the relationship between volts and ohms. And then we didn't work the problem. But voltage drop, everybody okay? So this is an ideal circuit. And then this right here is an actual circuit. So conductors do have resistance. Now it's very, very low, right? Like I said, it's rated thousands of ohms per volt. I'm sorry, ohms per volt. Ohms per feet. So these are gauge wires. We talked about wire gauge a little bit, right? These are the numbers of smaller gauge or the smallest wire. But if we look at a 20 gauge wire, what's its resistance per 1,000 feet? 12.8 ohms per 1,000 feet. So that means it would have 1,000th of that for 1 foot, right? And of course, we wouldn't be able to measure that with our meters, the standard a standard ohm meter. So the lowest scale on this meter is 400 ohms. So on the 400 ohm scale, I would not be, if I measured across this thing, it was only a foot long, it would measure 0 ohm. So this is why, now of course this is at a certain temperature. Unfortunately, they don't give us a temperature. So what determines the resistance of a conductor? So usually we start off with the material it's made of. And then we talk about the size, which we refer to as a gauge. And then 3, we do the length. And then 4 would be the material. I'm sorry, would be the temperature. And so one thing that this chart right here leaves off is the what? Temperature. So American wire gauge is given at a certain temperature if it deals with resistance. So this one says 20 degrees centigrade. So this is actually a better one. Free air, which means it's uninsulated, operating at 20 degrees centigrade, which is around 68 degrees. I have to do that. 68 degrees. Then this says a 50 gauge wire. They don't even write that. So the 24 gauge wire, which we deal a lot, has 25.67 ohms per 1,000 feet. This is copper. This is not aluminum. I wish they don't put that either. So the ampacity would actually be different for the two main conductors we have, of course, is copper and aluminum, right? You understand? Rule of thumb, by the way, is to go increase the size by 1 gauge if you go from copper to aluminum. Now, what NEC does is NEC rates it according to not only they rate it according to temperature, but basically they rate it, of course, according to what type of insulation that you use. Aluminum. A rule of thumb, if you figure out you need, so if I was going to run a 15 amp service in a house, instead of using 14 gauge wire, I'd use 12 gauge wire if I use aluminum. But we don't use aluminum anymore. What problem does aluminum have when we try to put it in a house? Anybody know? Huh? Well, the biggest problem we have is that it oxidizes real bad. So aluminum oxide, it rusts real fast. So that anytime we put oxide on a wire, then what happens is that, well, not all oxide. Silver oxide is a good conductor.
Sorry, I think it's real.
Oh, is this this is the, we're getting a new toy. This is the ampacity, and what does it say? Free air. What's that mean? It means it's uninsulated, and it's at 20 degrees centigrade. So what would you think would happen to the conductor when we insulate it? Would the ampacity go up or go down? Go down, because it's just like when you wear a coat in the wintertime. What do you wear? To keep warm, right? So what happens is that anytime I put current through resistance, and a wire has resistance, it produces heat. And what we want to do is we want to get rid of that heat. Well, what an insulator does, it holds that heat in. So what the National Electrical Code has done, or the 70 standard, which basically deals with the safe insulation of equipment. There's a lot of people think that National Electrical Code is for your safety, and it's not. The National Electrical Code is for the safe installation of equipment, electrical equipment, to basically help prevent wires. And so that's why OSHA, and then of course they came out with what we call the 70E standard, which is basically your safety. So what the National Electrical Code has done is we use a term called die rate. Die rate means you reduce the rating down for different situations. So we know that it depends on length, we know it depends on material, we know it depends on temperature, and we know it depends on gauge, right? You understand? So when we look at a 14 gauge wire over here, it says the ampacity of a 14 gauge wire is 32 amps. So that's the ampacity of a 32 gauge wire, but that's if it's uninsulated, right? You understand? And what? And it's at 20 degrees centigrade. But what National Electrical Code has done, originally their ampacity chart didn't make sense because they say on a 15 amp service we use 14 gauge wire. But if you looked at the ampacity chart, it said that it could actually count more current from that. So in this last version of National Electrical Code, they've made that correction. So what they do is up here, these are different types of insulation. That you can buy conductors for residential and commercial wiring. So that's the type of insulation. Now this temperature is not operating temperature. That is the temperature that the insulation is designed is safe to operate with. But you can see what they've done with a 14 gauge wire is they've rated it what? No, 15 amps. Unless I use this type of insulation. If I use this type of insulation, I can run it at what? 25 amps. So what they've done is they die rated this for the worst case scenario. So that means if my conductor's not over 100 feet, then what I can do is I can run this wire in any situation that we would run into in a residential situation and not exceed the ampacity of the conductor.
When you say die rate, it's basically giving it a...
It's reduced by. So if you looked at the code, when you get into commercial wiring, you start getting into figuring out how much you have to die rate it for different types of situations. So if you run the conductor through a boiler run, you have to decrease it by a certain percentage per degree. Then if you run it through the ceiling, if you across the roof, then you have to decrease the ampacity according to a formula that they give you. And anytime you reduce something because of a certain situation that exists, then we call that die rate. It's called a die rating factor, and they give you a multiple. And of course, here would be a fraction, like 0.9, and then you would take it and multiply it by 0.9, and that would be the amount of ampacity. So what that means is I might say, okay, it's rated at 15 amps, but when I start die rating the thing, all of a sudden I say, well, I can't use 14, I need to go to what, 12. And then we die rate that, and as long as it's less than what we need to carry, then it's okay. That makes sense? Everybody okay? So this is 310.15. It used to be 310.16. That is the new code book for some reason. What they do on the new code books, they like to move things around. I guess so you make sure you buy the new book. Power is rated as the rate of doing work in electricity. Power is measured in volt amperes or watts. We'll explain that difference later. So in AC, usually everything's rated in VA, especially in residential, and then of course DC, we rate things in watts. Okay, that makes sense. So what we do is these are our main power formulas. Getting at DC yet, you'll get into these. And of course, what we're saying is DC, you learn R. R stands for resistance. I'm sorry, my screen is bouncing. And then what we'll learn is, especially in conductors, we have something called Z, which stands for impedance. And X sub C is called capacitive reactance. And X sub L is called inductive reactance. And we'll talk about that in a little while. So the formulas that you learn in DC, what we would do is we would come in and for R, we'd either use Z or X of C or X of L, depending on what type of opposition we're talking about. Every one of these are opposition, and every one of them are rated in ohms. So what is ohms? Ohms is the opposition to the flow of current. And we have several types of opposition. Are we okay? Okay. So what power is produced in a load with 10 amp and 60 volts of current? Right? So this is volts, 10 amps. Then the power, P would be equal to V, which is 60 times 10. So we shouldn't need our calculator, right? 600. So this would be 600. And of course, we don't know what it is. It's either going to be watts, right? Or it's going to be VA, depending on what we'll talk about later on. What is the power produced in a load that has 133 ohms of resistance? So this will be watts at 50 volts. Well, here we'd use, it would be equal to 50 volts. So we know two things. So here we'll use V squared over R. Now, of course, you'd probably have to have a calculator to do that. Are we okay? Have I got your calculator? I don't have mine in here. Well, that's not true. I got the world famous Windows calculator. So that would be 50 squared divided by 133. So that's going to be 18.8 watts. Okay? If I did that right. What power is produced in a load with 5 amps of current and 33 ohms of resistance? So here we would use the formula. Where my marker is? Power would be equal to I squared times R. So power would be equal to 5 squared, which would be 25 times 33. And that would be our power. Oops. So that'd be 825 watts of power. Okay. Power and relationship between power, current, and voltage. Voltage and current are directly proportional. If voltage doubles to the circuit, current doubles, the voltage has current. Now the problem we have is most people associate power and current. So if I say, and I can do this in a class, I don't care how far they're along in the program, and I can say what happens to the power in the circuit if I double the voltage to the circuit. What happens to the power in the circuit if I double the voltage going to the circuit? It's going to go up by how much? Well, see, so you just proved my point. But power is equal to V times I. I is equal to V over R. So if I double the voltage, I double the current. So I double my voltage, I double my current. So power varies with the square. So if you double your voltage, your power goes up by 4 times. If you half your vote, if you triple your voltage, your power would go up 9 times. If you quadruple your voltage, your power would go up 16 times. If you half your voltage, your power drops by 1/4. So it varies with the square. It's 1 over the square if the voltage goes down. It's the square if the voltage goes up. But you'd be surprised how many people, you could ask just about any class I teach, And I don't put this power point up there. I says, what happens to the power if I double the voltage to the circuit? Somebody's going to say it's going to do what, Joe? Double, but you're wrong. So this is why we got a big problem with maintaining a voltage. Because if my voltage goes up, all the bulbs in my house are going to stop blowing, right? If my voltage goes down. I had my mother call me one day and she said, Rick, he says, my electric oven won't even boil water anymore. And I went out there and she was supposed to have 240 and she had 120. Well, no, she couldn't go up because the power dropped down by a quarter, right? You understand? 1/4 of what she was supposed to be getting. So her eyes wasn't even turning red anymore. And of course, what had happened, she had lost one of her lines from the transformer coming from the house. So I went out there and looked. So she had no 240 in her house. So odds are her dryer wouldn't work. Her clothes dryer would probably took forever to work too. So yeah, so it varies a lot. So this is why loads are designed to run. Most loads are designed to run at a voltage. So we have motors that are rated at your house. They're either 240 or they're 120. If you take a 240 motor and run it on 120, it probably won't even start. If you take a 120 motor and run it on 240, it's going to burn it up. Right? You understand that? If you take a light bulb that's rated at 120, you put it on 240 circuit, it's going to blow as soon as you hook it up. If you take a light bulb that's designed around 240 and you put it on 120, you probably won't even see it hardly come on again.
So I tried a little experiment out. I had a external speaker or a PA system, so I took the power supply from the old computer and I took 12 volts, just doubled it. I took it up to the 24 volts on the one speaker, and it ran fine. But I don't know if that's it's double that if I could.
Yeah, you couldn't put DC to the amplifier. I mean, you had to put it to the amplifier. That would be tricky.
But I was the other one the same way. And
And this is problems that's going to suit that. So remember, everybody okay on short? So what's a short? We've already gone over this, right? And what happens to the total resistance? Anytime we have a short, total resistance does what? Goes down. Total current goes up. No matter what type of short it is, right? You'll understand. So don't get a short. And that's what I said. Laymen or people, anytime they have problems with a circuit, they call it a short. And that's not true, right? You understand? Now my mama calls them shorties. I got a shortage. I didn't say anything to my mama because she's probably still thinking she's still alive. My mother was the punishment provider. She was the punisher. My dad had to spank me once, and that's all it took, right? So a short circuit occurs when two conductors coming from the source somehow get in contact with each other. And what's short? Shorts are caused by incorrect splicing, incorrect termination, defective loads, excessive current burning off conductor insulators, and conductive items falling into the circuit. So these are our main sources of shorts. Of course, what we're going to do doing in here is splicing and termination. The course is not quite right. It's called cable splicing and insulation. But we're going to teach cable splicing or conductor splicing and termination. So what's splicing? Putting two wires together. What's termination? To an end, bringing it to an end. So all conductors eventually have to come to an end, right? You understand? Have a denting. They got one function in life, and that's to get that current from the source to the load, or loads. So eventually they're going to have to connect to a load. They're going to have to connect to a source or to a load. And the act of bringing a conductor to an end, we call that termination. And the act of bringing it, hooking two conductors together, we call that splicing. The short circuits are very, very bad. We got to get short circuits. Are we okay? We already talked about the results. Something's going to happen. Somebody's going to give up. We talked about this in this class already, right? We talked about shorts in this class. Yeah, if you have a short, somebody's going to give up. It's either going to be what? Yeah, the power source is going to give up. This is where we got problems with regulated power supplies because they keep raising they try to compensate for a short. So they put more energy out there. But eventually they're even going to give up. So even your house, if you've seen where you got a short, your lights will dim down because now the power source is basically giving up. Usually not back at your power, it's usually dropped inside your transformers and inside your conductors. The conductors are either going to give up, and they're burning to right, understand, or your loads are maybe not going to give up because they might be the problem of the short. So what we do is normally we protect against shorts with overcurrent protection devices. The two overcurrent protection devices we use are circuit breakers and fuses. The big advantage of a fuse is they're really cheap compared per amp. And of course the biggest advantage of a circuit breaker is they're resettable. So in industry you're going to run into a lot of fuses. In your house you're going to run into a lot of circuit breakers. You still have fuses, but usually they're inside the units themselves. So these are fuses and circuit breakers. And of course these are the circuit breakers most of y'all familiar with. They run inside your house. We have single phase circuit breakers in our house. But in industry or in commercial situations, we run in 3-phase a lot. I'm almost sure we went through this before. Huh? Yeah. We talked about the different types of current, right? AC and DC. Are we okay there? And this is AC, which is really, really neat. So AC is generated on the principle of a circle. So if we move this around, what you do is you get what we call the vector sum. So you notice that this is the center. We always can drop a vertical down and perform what we call a right triangle. If I can stop this. Oop, they want to stop there. That's good. So we can drop this down, and this forms what we call a right triangle, which means this guy here is 90 degrees. What's the sums of an angle and all the angles in the triangle? What it's always going to be? Always going to be 180 degrees. So what that means is that means the ratio of these sides vary exactly according to this angle right here, which we call the angle theta. And what we can do is if I know the length of this side, then I can calculate the length of this side, which is the actual amplitude of the wave, by using some trig. And we call it this, we could take the sine of this angle that we call theta. And that's the abbreviation. And we can calculate this, which would give us the actual amplitude of the waveform. We call it the instantaneous. For that reason, we call this waveform a what type of waveform? It's called sine wave. Because the amplitude, Rich, not a waveform, It's like when Sarah Verser came out here and recorded y'all see that? She called it what? Megatron. Yeah, called it Megatron. And it's actually Megatron. But a lot of people hear that. They hear Megatronics. So we got to get ahead. We got to get in. So this is called a sine wave. So this is what Alabama Power generates. And we talked about cycles, right? We talked about alternations, frequency. We talked about that, right? Three-phase power. generate 3 different waveforms that are 120 electrical degrees apart. And basically, this changes all our power formulas. So when we start dealing with 3-phase, so what happens is the phases are spread out. The current is vectored between these 3 phases. Well, we can't really say leading or lagging in this situation, because we could say, if we call one of them A, which would be this one, we can say this one lagged. We could say that one lags by 120 electrical degrees. And then this one, which would be phase C, would be 120 electrical degrees away from phase B. So we could say that, but normally when we use leading and lagging, we talk about capacitors and inductors. Well, what happens is now I'm adding another conductor. So when we send 3-phase, we have to send it in at least 3 conductors. But what we get, if I was to come over here and measure that current there, and I would measure that voltage there, we know that power is equal to V times I. But the problem is we're spreading it over 3 wires. So the actual formula for 3-phase is V times I times the square root of 3. That's what it is. So basically, we add one more wire, but we carry times the square root of 3, or 1.73, more power on 3 wires. Now, 3 wires are very expensive, but, you know, if I'm transmitting it, it's easier to run 3-phase than single-phase. But when I get down to low-powered applications where I'm not trying to do a lot of power, then we drop down to single-phase. So your house runs single-phase. But if you go to some big commercial place, it's going to use what? 3-phase, because they use more power, and it's more efficient for Alabama Power to deliver that. So the cost of the extra conductor would offset the cost of, or the power savings would offset that. So this is why these big we call them high tension lines. You're going to see 3 wires, right? And this is power and AC circuit. We looked at this, calculated that out. Talked about root mean square, right? We okay there? Yeah. Well, the problem is that when we use conductors, we're dealing with 2 types of current. We're either going to put AC current through the conductors, or we're going to put DC current through the conductors. Now, conductors are going to do 2 things for us, and we'll talk about that in a minute. They're either going to handle power, or they're going to handle signals, or both. We can combine them. We can put signals and power on the same wire. Power, we understand what power is, right? That's what actually is delivering the power that we're consuming. But we're going to do things. So I go out there and I look at my car or my vehicle, and we got an antenna somewhere, and it's got a conductor that's running from the antenna down to my radio. Well, that's not a power wire. That's a signal wire, right? That's used to handle signals. We got all this networking cable running all over this building. What's those for? That's not power. That's what? Signals. We got fiber optics. Fiber optics can't handle power. So fiber, we're sending nothing but what? Signals. And we use the term conductors in there too. So some wires are designed to handle signals. Some wires, the conductors, are designed to handle power. And of course, some wires are designed to carry both of them. So I got if anybody still have a phone in their house? Well, I do. And there's 2 wires going to it. And you don't put any batteries in there, so that thing is carrying both your power and your signal. And that's been done for years. We had crane operators that they hooked their their mic system was hooked up to the hot rails. We call them hot rails because that's where it transferred power from the power over to the crane that's in motion. And they carried their comm systems through the hot rails. So that way they didn't have to have any wires actually looped and going to the crane, because them cranes would.
There's wires out there now that carry power off the
Yeah, well, that's our phone. So our phone system here carries the power off the Ethernet. So to run our phones, we can't run it through a switch or anything like that unless they bring the power through, or you have to put a plug in it. So when we start adding XML and XFC, so unlike resistors, reactance varies with frequency. Devices called capacitors, as frequency goes up, passive reactance goes down. Devices called inductors, as frequency goes up, inductive reactance goes down. So we got two things that are basically opposite of each other. It's kind of like parallel and series circuits. So just about everything you say about a series circuit, you'll reverse it when you talk about parallel. Well, that's the same thing true with inductors and capacitors when you put AC on them. So we put AC on these devices, then the amount of opposition they have is proportional to the frequency that you put them in. So that means if we double the frequency on a capacitor, the capacitive reactance would halve. If we half the frequency on a capacitor, the capacitive reactance would double. If we put DC on a capacitor, it's going to block it. So on a capacitor, if we put DC on a capacitor, it acts like an open. On inductors, they're just opposite. As frequency goes up, their opposition goes up. If frequency goes down, their opposition goes down, but they're directly proportional. So if you double the frequency, then the opposition would double. If you half the frequency, it would half. If you put DC on an inductor, it acts like a piece of wire. Now, when we start combining resistance and capacitance, when we start combining resistance and reactive devices in a circuit, we call that opposition impedance. But you're going to find out that most of the people in AC call the opposition in an AC circuit, they call it impedance, even though there is no reactance in there at all. Now, what happens when we start combining these things? This is not a formula you need to know. It's going to pop up here in a minute because conductors, if we put an AC on a conductor, we're going to set up a capacitor, almost unavoidable. And we're going to set up inductors, almost unavoidable. We call that stray capacitance and stray inductance. These are stuff you ought to, that's not deliberately put into the circuit. And we were talking about this, right? That's the formula. You can see why it changes. So we buy a capacitor that you call ferrites, which would be C right here. And then F is for frequency. And then this is a constant right here. And in AC, you'll learn why we use 2 pi because it's generated on a circle. So that means if this is on the bottom, if this right here doubles, then this right over here is going to halve. So as frequency goes up, X of C goes down. Now the size of the capacitor don't change, but the opposition changes, which is really, really neat. And what we can do with these things, guys, is we can use them for filters, which means we can get rid of frequencies that we don't like. So if I want to get rid of a high frequency, I can use a capacitor. If I want to get rid of a low frequency, I'll use a what? An inductor. This is what we used to use to tune our TVs, tune our radios. Is we use these two things. So they're exactly opposite of each other. So what that means is if we put capacitors and inductors in the same circuit, they will cancel it. They will have a tendency to cancel each other out. We call that a resonant frequency. So used to when you was going out there and you were tuning your radio on your car, you can't see it on TVs, but your radio in your car has frequencies up there. Well, that's what you used to do. You'd have a capacitor that you would tune, and you would have an inductor that was fixed. And then what you would do, or variable, and you would tune the capacitor until you set up a frequency that would pass that frequency. And what would it do with all the rest of it? It'd cancel them out. Now we use the problem we have with that though is capacitors and inductors vary with temperature. So I don't know if you remember that, but you used to have a fine tune on your radio and your TVs. And what you'd have to do is you'd listen to it a little while and then it would go out and you'd turn the little fine tune and you'd pick it back up, because what was happening was your capacitors or your inductors were changing with temperature. What we use now is an electronic circuit called a phase-lock loop, and them suckers don't drift. They maintain a resonant frequency electronically. So now if we put it on this station, it don't change unless we get out of the range of the station. So used to all these devices, all your TVs and everything had a fine-tuned thing on there. We have one of our instructors that has an old radio, and it's still got that stuff on there. He brought it over for me to fix.
I found art is at a scrapyard. They were like push it down to the top. It still works.
Oh, it does.
Yeah.
We can't pick up TV anymore because they don't broadcast. Everybody's gone to digital on your TV.
Yeah.
Your radios are still, most of your radio broadcasts are still analog.
Pick up much AM station.
Yeah, because they're migrating over. Just about everybody's a migrating.
Yeah.
Except for Lawson. Lawson broadcast. They're what do they call it? They're still on AM. Yeah.
Yeah. I need to convert it.
So, and this is inductors, and this is the formula for inductance. So the frequency goes up, XPL goes down. And this is just nice to know. All we need to know in this class, if frequency goes up, XBL goes up. If frequency goes down, XBL goes down. So this means we got to be really cognitive on the placement of conductors, because if they get in close proximity together, that sets up a capacitor. If we put loops in it, it sets up an inductor. And of course, DC has no difference. So we can loop a DC conductor as many times as we want to, and all we're doing is changing the R of the conductor. The more length we use of a conductor, R goes up. So these are purchase capacitors. Now, what's neat about these devices, I don't know if they're in here, but what's neat about these devices is they create phase shifts. So I have a capacitor here. It's a variable capacitor, by the way. Did I bring my camera up? No. Look at that. So I thought I did. Where's my camera? So this is a capacitor. So basically all you do on a capacitor is you have two metals that we call plates. So you can see these are nothing but plates. And then we have another one that we call a second plate down here. And what you're basically doing is just bringing them in close contact. They don't touch, but all you're doing is bringing them in close to each other. Now what happens is when this is minus, this is plus, and it sticks up an electrostatic field between the two, what we call plates. Now what determines the amount is how close you can get those plates together and still keep an insulator between them. So a capacitor, what we have is we have two conductors we call plates, and then we have an insulator between them. Now the insulator this guy's using is air. Air is a pretty good insulator. And what determines the amount that we can get is how close we can get those plates together. What we use as that insulator, we call it a dielectric, and how big the plates are. Now what we're doing here is we're adjusting the overlap of the plates. So if I'm out here, if I can get this on my camera. So if I'm out here, that means the capacitor is only where the plates overlap. So this is one way that we can make a capacitor variable two different ways. We could have a screw where I adjust the distance between the plates, or I could have something where I adjust the overlap of the plates. So the capacitor would only be this amount right here. So the more I overlap it, the capacitance would go up. The less I overlap it, the capacitance would go down. So that's the way it is. So this is actually a tuner out of an old radio. So that's all we did on this one is we adjusted the capacitor and we set up that tune circuit. So we got a knob over here. So, but when I come over here and look at the scope, so the circuit I have is a pretty simple circuit. Where's my PowerPoint there? Right here. So the circuit I have is I have a capacitor. This is a symbol for a capacitor. I don't like using that one because this is a symbol for a capacitor. And then what I've got is I've got a 1K ohm resistor, and then I've got an AC voltage source. And what we're doing with our oscilloscope is we're looking all the way across the thing, and then the other probe is looking across the resistor. And then when we come up and look at the actual display, you can see a watt in there. You can see a phase shift. So, where's my meter? I need that. So what we're doing is we're looking at the voltage at two places in a circuit. So the yellow is the applied voltage, and then this is inside the circuit. So what we really create is we create what we call a phase shift, which is pretty neat. So we use this feature. If we didn't have a phase shift, there would be no such thing as a single phase motor. Because to cause that rotor to turn, your magnetic field has to shift. So what we have inside of single phase motors, we have a special winding called a start winding that we deliberately create a watt in it, a phase shift. So what happens when this guy right here starts down, this guy right here is coming up, and it causes the magnetic field to shift, and what does the rotor and the motor do? They turn. So we have what we call capacitive start motors, and that's what they are. Now once the motor's in motion, then it creates the phase shift itself. So what we do is we start the motor and then we click out the start winding. There's what they call a centrifugal switching. So this is a capacitor. So what I'm doing is all I'm doing is I'm changing the overlap of this thing. And you can't hardly see it, but I'm not only changing the phase shift, but I'm also changing the voltage drop across the resistor, which is pretty neat. So that's all I'm doing is changing the capacitance. So this is a variable capacitor. So when I come up here and turn this knob, if I can get it right, you see what happens is this set of plates are sliding into this set of plates. And then so what I'm doing now is I'm increasing the size of my capacitor. Here I'm decreasing the size. So this would give me a range. This is going to be between so many farads and so many. So what does capacitors cause? Well, one thing, they cause a voltage drop. They appear to cause work. So if I was to measure the current flow in and out of the capacitor, I would have a current and I would have a voltage. So you'd say, okay, power in the capacitor would be equal to V times I, but the current is not flowing through the capacitor. The current is flowing in and out of the capacitor. So we are actually getting absolutely no work out of this thing right here. It will not, capacitors don't get hot. So if they don't get hot, it means they're not doing any electrical work. So we end up with two types of power in the circuit. We end up with what we call true power and apparent power. And this is what you pay for. You pay for apparent power unless we do something. So anytime we get capacitors, and now if I was to put DC on this, I'd have no voltage drop across the resistor because DC sees it as an open circuit. We got to have AC to get this what we call capacitive coupling between the two plates. Are we okay? Oops. I installed Skype on my computer so I could talk to my wife when I was in Germany. Worked out pretty good. It was a little bit of delay because of the bandwidth of the hotel we was at. So normally it'd be kind of like when the movies in the mouth get out of sync with each other. So you'd hear them and you'd see their, because video takes a bunch of bandwidth. We could do the same thing as an inductor. What was so funny, I couldn't find my coil of wire, but I had a coil of wire and I could unroll it and the two signals would be in phase. And then what I would start doing is I'd start looping that wire, and you'd start seeing a phase shift. So all an inductor is loops of wire that are in close proximity to each other. So what we end up with, guys, in an AC circuit, we end up with two types of power. Delivering AC voltage and current out of phase makes the source deliver more power than the actual working performed by the load. The out of phase power being required from the voltage source is called apparent power, and this is in units called volt amperes. So if you look at a transformer, you'll never see a transformer rated in watts. They're all rated in volt amperes because your transformers have to deliver apparent power. The power required to perform the work delivered by the load is called real power or true power. Real power is in watts. The power factor is the ratio between the power and the true power. This is what, so if you had a power factor of what we call 1, a lot of people call it 100%, it means your true power and your apparent power are equal to each other, and that's what we want. Huh? But we get close. Alabama Power requires a power factor of at least 95%. Now they compensate for the power factor at your house. So that's why when you get your power bill at your house, it's in watts, kilowatts. So you are paying for true power. You got to be real careful because you can buy these little capacitors that you put in your light sockets that's supposed to help your power factor. But if you go over one, it's just as bad as being under. So you'd end up paying more than what you're actually getting. So we have different methods. We can the power grid is predominantly inductive because all your transformers is nothing but a coil of wire. All your motors are nothing but coils of wire. So the power grid is primarily inductive, which means your current is lagging behind your voltage. Well, what we find out is capacitors and inductors cancel each other out. So every once in a while, so in your power, in the substations, they have a dynamic unit that basically brings more, switches capacitance in and out of the circuit to compensate for the power factor. But if you get to a big company like US Steel has their own substation. So US Steel is responsible for their power factor. Now you would think Alabama Power would like you to have a bad power factor. But you got to understand their whole transmission system has to support apparent power. So if you got all these companies out there running a bad power factor, then Alabama Power would have to put bigger transformers out there. They would have to put bigger generators. They would have to put bigger conductors. So Alabama Power don't want you to run a bad power factor. And that's why they require at least 95%. If you get below 95%, they charge you extra. So you get paid a penalty. So US Steel's got their own big capacitor banks out there on their substations that they switch in and out. And there's also a motor, and they can do it dynamically too. One of the things that can dynamically do it is a synchronous AC motor. So when I worked out there, Alabama Power had 2 synchronous AC motors that didn't need to be synchronous. They basically use it just for what? Power factor correction. If you overexcite the things, they'll want to lead. If you underside it, they lag. So they basically they run those all the time. So they monitored the power factor. If it got down too low, they would just overexcite those synchronous motors and get them back on. And that's the problem you have with a big company is they're constantly changing your power factor because they're turning motors on and they're turning motors off. And so anytime they turn a new motor on or put power on the motor, it's going to cause it to lead and lag. So DC is more efficient to transmit, but the problem with DC is we can't step it up and we can't easily step it up and step it down. So, if I could get 75,000 volts DC, it would be easier, it would be more efficient to send that because now we're only worried about the resistance of the wire. We're not worried about X of L and X of C anymore. We're not worried about impedance. And there's a lot of there's a tendency to move back to DC on real long distance lines where they electronically make DC, and they send it on. But then they get it. But when they get on the other side, they convert it electronic and convert it back to AC. So I think the big power lines that run between on the English Channel over there are DC channels or DC lines. But the problem with DC is we can't easily do step it up and step it down. But when we start working with AC, we got to worry about through power and apparent power. Now, apparent power only comes into play with AC. DC conductors, all we got to do is worry about the resistance of the wire. That's all we got to worry about. If a power source is supplying 80 VA to a circuit and performing work, so what it is, it's true power. The power factor is true power, which is 80, divided by 100. So our power factor would be equal to 0.8. But just about everybody don't use the fraction. They would say 80%. And that's usually they give power factors in percentage. And luckily, you don't have to worry about it unless you get into wiring AC circuits. Conductor terminology, this is very important for the class. So we use what we call a trace or a foil. What are these conductors? Yeah, these guys are extra printed off a printed circuit board.
Oh, okay.
We call these traces or foils. Those two terms are interchangeable with each other. Right? When you look at a printed circuit board, like Thomas has got there, you see all these conductors running all over the place. We have what we call single-sided boards. These are boards where you have a component side and then you have the foils are on one side of the board. We have a double-sided board, and when we talk about double-sided, it means the traces are on both sides. And then we have multi-layer boards, which means there's traces running in the center. So these are most of your computer boards. So odds are the board in your cell phone is a multi-layer board. We have what we call a conductor. Now this is usually when you use the term wire is supposed to be an uninsulated conductor, and then our uninsulated conductor of electricity. And when we use the term conductor, it's technically a wire that's inside a wall, an insulator. But most people call them conductors, or most people call them wires. So these two terms can be used interchangeably. Then we have a cable. What's a cable?
Group of wire, group of insulated.
That share a common jacket. Now this is evolved. This has evolved over the years. I need to go back and change this, by the way, because a lot of times we'll see a cable and it's got one conductor in it. And inside the glossary, I have changed that. For a cable, or a conductor, or a wire that has multiple layers. Like coax, we call that a cable. Well, that technically is a cable because it has two wires inside it. But we got these high voltage cables, and they're extremely high voltage. And the problem we have with voltage is that voltage is pushing electrons, and those electrons are looking for ground. So anytime I get a high voltage cable close to a ground potential, what happens is all your potential tries to move on that side of the ground. So what that means is if I've got 50,000 volts and I've got insulation rated at 75,000 volts, but that's 75,000 volts all the way around. If you move that 75,000 volts over to one side, then the insulation will break down. So what they do is they put layers inside that high voltage cable to keep to keep the potential in the center of the cable. And so we call those cables because they're built out of multiple layers. So you have one wire, and then you have multiple layers of insulation in there for protection and all this other kind of stuff. So multiple layers, I don't know, I can't remember how to say it, of insulation. Slash multiple built with multiple layers, I guess. I guess protection. So we'll look at a fiber optic cable. Basically, it'll have the conductor, and then it'll have a coating around the conductor, and then it'll have a jacket around the conductor, and then it'll have Kevlar around that, and then it'll have a jacket around that, and we call that a cable. So it's built out of multiple layers of protection. So what we're trying to do, so we call those cables too, and that's a legal term.
On fiber optics, would it be a deep line running on the house?
Well, no, it depends on what type of bandwidth you're trying to send, and what the bandwidth is coming from. It would be a waste of time to take what I'm getting from the cable company and try to run fiber optics through my house.
Yeah.
Because they're only pushing, about the best you're going to get. I think Spectrum's at saying 100 megabits now.
They're getting ready to force my parents on the fiber optic. Yeah, they're about to run fiber optics through our neighborhood.
Through your what?
My neighborhood.
Yeah, but it's not. Oh, and they're going to come to your house.
So I figured if we could run fiber optics from wherever their access.
If you're still going to use standard routers and you're still going to use standard stuff, then getting it inside your house would be a big waste of money. Of course, you could run plastic in your house, and we'll look at this in a minute. Stranded. What's stranded? I'm sorry. Solid strand. What? One solid conductor. Then we have what we call stranded. What are they? Twisted, not necessarily twisted. I need to take that out too. We have different methods that they do twist some of them. The bigger the stranded cable is, the more likely it's going to go to a twist. The smaller the cable is, it's just going to be straight multiple strand wires.
I slipped on the wire that's set gauge or solid set gauge.
Yeah, I think you showed me,
Yeah.
which I've never seen. Usually stranded, the gauge is slightly bigger, but not much. Stranded has the ability, but it's not nothing that we can measure. The ampacity for stranded is a little bit higher than the ampacity for stranded, but it's nothing that we need to understand. So what would be the advantage of stranded over solid?
Stranded,
Flexible, that's it. It's flexible.
Terminated.
Yeah, solid is easier to terminate and splice. So what we do on solid, a lot of times to splice it, we just twist wires together. Put a wire nut on it. Stranded, we have to make sure, because if you lose one strand, you change the gauge of the wire. So we'll look at a thing where we're specified how many strands of the wire we can legally cut. If you got a solid strand wire, how many can you cut? None. 2 strands you can't cut one because you have the ampacity of the wire. So the more strands you have, you can nick them a little bit and they can cut them, but you got to be really careful. Solid strand, we don't have that part. But solid strand, we can terminate them real easy. We can wrap them under a screw. We can tighten the screw down. We can't do that with stranded because if you put it on that screw, as soon as you tighten it down, we call it bird caging, which means the strands are going to spread out. And if one strand gets out from under that screw, what did you just do? Change the ampacity of the wire. So that means stranded, we're going to have to either tin the wires and turn them into stranded, or we're going to have to put them inside what we call a compression sleeve, which basically holds the sides together. So even if it bird cages, it can't get out from under there. Or we got to put some type of terminal on it. This is a printed circuit board. And this is just a small one, guys. These are conductors. This is actually not a desktop computer. Did you ever get that working? These are cables. So we have round cables, we have flat cables. These are also called ribbon cables. Huh? Stranded and solid. Are we okay? Conductor splicing. We've already talked about this. Permanent or semi-permanent joined two or more conductors together. Termination is the act of attaching a conductor to a final destination point. Either a voltage source or load, right? Conductors, these are what? Power cables. Are there signals cables? Right? I understand the difference between the two. Yes or no? Everybody okay? Okay. We're going to be using meters a lot in this class, so we went ahead and added these. And by the way, we're going to make this available this term. You've already had DC. You already had DC? Are you taking it now? Taking it now? Okay. Okay. Well, then you'll want to set on this. What we do is we order a free certification. That's NC3. That's what this Siemens card is. The Snap-on card is over there, where you can get a certification in the use of a meter. We're doing it in DC, but you've already had DC. So what we're going to do one Friday, we're going to set it up where the people who's already passed DC can come in and set in on the training for that meter certification. And then to get certified, you have to take a test. How many questions on it now? I don't know. Did you get yours? Yeah. It's a good deal. So that's a certification that you could put on a resume, you know, that you're meter certified. NC3 meter certification. But what they've done is, for years, if I look at this meter right here, I've had this meter for eons. No, it's a Spirit. It's a really good meter. I really like it. And this meter is basically not rated. Basically, it gives us a voltage rating and a current rating. But what has happened is a lot of these meters, people have problems with them where they'll get into a circuit and then a big energy pulse will come in and then the meter just disintegrates and blows up. So what they've done is they came out with different categories on where these meters should be used at. And basically it protects you against, if you get a meter that's got a, you know, it's got a 2,000 volt AC scale on it and you put it in 50,000 volts, and it's because of stupidity. But if you get a meter that's got a 2,000 volt range on it, and you put it in there into 1,000 volts, and you get an 800 volt spike, then that's not your fault. And we get spikes in industry all the time, just them unloading and unloading the lines. You know, they run different lines all the time. You get spikes coming in there, and your meter, you might be using it in the right voltage, but if you get enough high energy spike, the meter could still blow up. So what they started doing, probably, I don't know how many years ago, is they set up what we call meter categories. So we have what we call a Cat 1, Cat 2. Don't get this confused with networking cables. So we have different categories of networking cables too. And we'll look at that when we get to that. But meters, we have different meter categories. And what this does is this gives us a rating of how much surge the meter can handle. So we have what we call a Cat 1 meter. And this tells you where you're usually using it. So the further you get away from the power source, the distribution, the more stuff you have to go through, and the power would dissipate strictly by basically the inductance of the system. So if we're out here working on electronic equipment, then we can probably use a watt, a Cat 1 meter. If we're up here working on single phase, we can use a watt, a Cat 2 meter. If we're working between the distribution and the load, then we can use a Cat 3 meter. If we're working on the distribution side, then we need to use a Cat 4 meter. That makes sense. Okay. And these are the actual ratings right here. These are the surge ratings. So that means a Cat 4 meter. So people think a Cat 3 meter rated at 8,000 volts is as good as a Cat 4 meter. So they say a Cat 2 meter rated at 6,000 volts is as good as a Cat 4 meter rated at 6,000. That's not true. So a Cat 4 meter would be rated at what? 8,000. So this would be the equivalent meter. So what that means is the higher the Cat rating, the more surge you can handle at a higher voltage. Does that make sense? Now this does not determine the maximum range on your meter. This is the surge above the maximum range. So that means if I've got a Cat 4 meter and it's got a range of 2,000 volts, then it could handle a watt. I'm sorry. If it's got a rating of 1,000 volts, then it could handle a surge up to what? 8,000 volts. Above 1,000 volts. Right? You understand that? So a Cat 4 meter would be a lot more, would cost more, but it would give you more protection. Now, what do you want to buy? Well, most meters, and I need to go get mine. I think this is it right here. So this came out later. And this right here, so this right here is a Cat 2 meter. Now usually your category rating is down by your terminals. We're going to focus on that. It's a Cat 2 right there. And then down here it gives you the maximum voltages that we can go. So DC I can go up to 1,000 volts. AC I can go up to 550 volts. So I don't know if that's on the chart or not. We'll see. Cat 2. Yeah, this is the rated voltage. So it's going to be able to handle maybe a 4,000 volt spot. That Cat 2. Because this don't show a 750. The AC has a rating of 1,000 volts. So this guy here would be able to handle a 6,000 volt spot. That's the maximum rating. Most of your meters are going to be a Cat 2, Cat 3, or Cat 2, Cat 4, Cat 3, Cat 4. Where the Cat 4, they might rate it at 2,500. Cat 2, they would rate it at 4,000. Which means on so it was a Cat 3, Cat 2. So your Cat 2 might be rated at, no, it'd be backwards. It would be like this. So what we would do is we would drop back one scale, right? Does that make sense? So y'all can look at this one. This is still an older meter. I don't think I've got it. What's your?
I've got a over here.
Oh, Roddy died.
Part of the Cool Club.
Yeah, let's take a break, guys. I know we went over, but. Are we okay on category meter?
Yeah.
So for this class, you need at least category 3 meter. So you can get a Cat 2, Cat 3. The maximum voltage that you'll use here at the college is 220 volts. Multimeter, so making measurements, what we call a multimeter. To be classified as a multimeter, you gotta do at least three things. You gotta do voltage, current, and amps. Voltage, 3 meters, voltage, ohm meter, and ammeter. So we look at these meters, they got at least three functions on them. But it's like cars now. What do they do with cars to make them more sellable? Add more crap, yeah. And that's a perfect analogy. So this guy here, it'll measure AC volts. This is what we call a manual ranging meter, which I like because that way I know where I set my range. I'm not depending on my meter to set a range. Yeah, so what you got to do on those, you got to look at the meter to see what it's on. So it's got these ranges of AC volts, these ranges of DC volts. Then it's got DC amps, then it's got AC amps. Then it measures it measures temperature. No, this don't measure temperature.
Oh, really?
No, this measures C. So these are capacitors. Then it measures frequency. That's what the kilohertz is. Farads, right. It does logic, so it does highs and lows. And then it checks out bipolar transistors, which we call PNP and NPN. What you have to do is you'd have to insert it right in there. So that's your multiple functions. But to be a multimeter, it's got to do at least three. It's got to have at least 3 meters in there. We call them ammeters, ohm meters, and voltmeters, right? So when you say, what do you use to measure voltage? This is a test question, by the way, and it says a digital multimeter. You got a voltmeter down there, and you got a digital multimeter. Digital multimeter answer is wrong. Because you've got all those different meters in this one meter, right? You understand? So to measure voltage, you use a voltmeter. So you would come up here and you select voltage. You wouldn't select current, right? You understand? So be careful on that question. I put that on any question. I've seen students miss that so many times where you have a voltmeter down there. No, don't take these chairs over there. You got plenty of chairs over there. Don't take these chairs over there. Leave them over here. Leave them over there. What happened? So a voltmeter, place the meter across the device to be measured. We use it to check for correct voltage or to verify a circuit is being energized. Very, very important. That's part of the safety. So even if you pull a disconnect, the first thing you should do before you start tearing things out is get that dang voltmeter out and make sure you pull the right disconnect. Or the disconnect could be bad. I've seen disconnects actually go bad. Ohm meter. Only made with power removed from the circuit. Measures across the device to determine the resistance. Ohm meters do not tell you reactance. That's the biggest problem. You don't have a meter that does reactance. All we can do is resistance. Ammeters. Open the circuit and place the ammeter lead across the open that you just created. The current must flow through the meter. So which ones do you think we use most often? Volts and ohms. Because ammeters, you have to do what? You have to break the circuit to put the meter in there. Because to measure flow, you got to put the flow into the meter. Now we do have another meter called a clamp-on. I thought I put it on. They call it clamp-on ammeter. Some people call them a tone meter. Some people they have different names. But what you're doing when you do these guys, so we've already talked about when we put current through a conductor, it generates a magnetic field, right? Right? Did I show y'all that? Yeah, I picked up my X-Acto knife, didn't I?
Yeah.
And then, but to create if it sets up a magnetic field, that magnetic field is directly proportional to the current flow through that. So if I had a method or something that I can measure the magnetic field, then my meter could translate that as what? as a current. The only problem is, to get that, we have to induce it, so we have to use AC. So, these things usually only work in an AC circuit. We do have some that they measure DC, but they use a special sensor called a Hall effect sensor, which we'll talk about when you take the sensors class. I think the sensors class is required in both programs. What's that? Yeah, we have different types of overloads. We have heater overloads, which the advantage of a heater overload, an overload is a device we put in a circuit that detects if the motor stalls or if a motor pulls too much current. The problem we have with motors is they pull a lot of current when you start them. So your overcurrent protection devices have to let start current come through. Well, if the motor stalls, it's going to pull that start current. So what would happen is your fuses are rated to let the motor start. So if it stalls, it's going to burn up. So we add another circuit that we call an overload, which basically looks for if the motor pulls too much current over a certain amount of time. And if it does that, it'll trip out the control circuit. We have heater overloads. Now, the advantage of heater overloads is that they work off heat and they're very cheap. Then we have what we call electronic overloads. Electronic overloads usually use something very similar to a clamp-on ammeter. It uses what we call a current transformer. They call them CTs, which basically works on the same principle. But so a clamp-on ammeter, what you're actually doing is you're not measuring the current, you're measuring the strength of the field. We got a couple of clamp-ons. They're still called clamp-ons, but they're strengthened. But those are not ammeters. Those are clamp-on ammeters, right? So a true ammeter has to be what? Put in series. No, you just put it across, around. Yeah. This would be in series. To put it in series, you literally got to break the circuit and bring the circuit into one and the circuit into the other. You have to put it across. You have to put it across the wire. But it's not in series, right? Huh? The what? Oh, for 4 to 20 for current loops. I don't know what these guys source. This guy does pretty good. This guy will light an LED, which is pretty neat. Now this guy here won't. This guy here will. So that means this guy here puts out at least 20 milliamps.
Yeah.
The snap-on meters will light an LED too. So voltage measurements, what we do, we put, by the way this is written up, and this came out of a book, is we have 2 leads on our meter. We have a black lead and a red lead. What's the black lead? Huh? Meter column. Meter column. That means your measurements are made relative to this lead. Now in AC, it makes no difference because AC has no polarity. So it makes no difference how you hook a voltmeter up or even an AC ammeter up in an AC circuit. And really, really slow. But then it's just going to give you problems anyway. So this is your meter common. And this is the lead is going to measure relative to that common. So this lead is going to be relative to that right there. So what that means is in a DC circuit, we had to really, really honor polarities because on an analog meter, you had a pointer dial on it. And what would happen if you hooked it in backwards, the pointer dial will peg out against a stop, and it could bend your dial because it's really, really thin to get a real accurate reading. And if you bend it now, your meter was reading one thing and your scale was reading another, right? But when we came out with digital meters measure minus negative voltage just as good as they measure positive voltage. So if I was going to go through a circuit, a series circuit, which is like this, then what I would do is I might start off, but I'd put my meter lead right there and put it right there, and then I'd swing that one over there, and then I would swing that one over there. So I wouldn't go like that. I would. And so what you realize, if on a DC circuit, if your red lead points toward the positive, your meter's going to measure the same voltage, but it's going to be negative. If your black lead points toward, if your red lead points toward the positive, then your measurements are going to be positive. But still, the voltage is going to be the same. So a lot of people get tied up on that, right? But you'll find out later on it's a good habit to putting your common lead somewhere and leaving it alone. So this says voltage measurements. If possible, do what? Remove voltage from the circuit before you put your meter in, if you can. Sometimes you can. Because this is what happens. You don't have your meter set right and you stick the sucker in there, you get this little arc in there. Once you create an arc, you create ozone. Ozone has a real low resistance. And so just hooking the meter up sometimes causes what we call an arc flash. So if you can, turn the meter off. Turn the power off to connect your meter. Especially if you get up, what's the lethal voltage? What do they consider lethal voltage? 50 volts. It's considered to be anything above 50 volts is considered to be lethal. It don't mean it's something below 50 volts can't be lethal, but anything above 50 volts is considered to be lethal. And so what they would like, if you could, you need to do that, but very few people do that. Especially if you're working in a plant. You turn off voltage, what's going to happen? You're going to shut somebody out. Select the correct voltage, either AC or DC. Because if you don't, if you put it on DC and put it in an AC circuit, guys, what's it going to measure?
Oh,
zero. Because it's going to give you the average of this guy right here. Well, the problem is I have a positive 1 volt. I have a negative 1 volt. If I average a positive 1 and a negative 1, it comes up to get 0. So what the DC average of a sine wave is 0 volts. So if you put your meter on DC and you put it in an AC circuit, it's going to measure what? 0. If you put it on AC and put it on DC circuit, it's going to measure something, but it's going to be wrong because of the circuitry it goes through. So that's why we had to use the root mean square to come up and get what we call the effective voltage. So normally what we do is we put the black lead on the common, we put the red lead on our measurement. Power's off, turn on power, record the reading if possible, remove power if possible. But this says power's off, so this doesn't. What you should get in the habit of doing, guys, is anytime you turn off power, before you put your hands in that circuit, you need to get your meter out and check to make sure you don't have much voltage there. Now, in an AC circuit, you will always measure something because of what we call induction, capacitive coupling and induction. So very seldom in an AC circuit, when power's off, do you measure exactly 0 volts. And we refer to it as a go flow. But it's going to be a lot less than the voltage you're trying to measure. DC, if you turn power off, guys, you're going to measure 0 volts. So this is an example of the way we connect the voltmeter, right? Current meter, what do? We always put a current meter in there, though, or an ammeter. We always turn the power off. We open the circuit somewhere. We put our meter, we replace that open with our meter. Then we turn the power back on. Make sure you have your meter set right. Make sure you have it on the right scale. Most meters now have high current and low current. So this meter right here has a 10 amp and then a milliamp. So if I'm measuring 10 amps, if I'm going to measure anything up to 10 amps, I'm going to put my red lead here. If I measure anything below 10 amp, back in the milliamps, I'll put my load here, right? Because it uses a different shunt. By the way, People don't understand that the only thing the actual meter measures is volts. That's all it measures. So what we do in the circuitry, so what we use on current is we run it through something called a shunt. And then what the meter does is it measures across the shunt. So this is where we can connect the meter. So this is for a panel meter. This would be a meter that's up on a panel somewhere, and you don't want to bring 50 amps up to a panel. So what you do is you put your load across this guy, and then your meter is right there. Now this is a 50 amp shunt. 50 amp shunt, and it measures 50 millivolts. So this guy right here would only drop, this big chunk of copper would only drop 50 millivolts at 50 amps. Understand that? So 1 millivolt means it would be 1 amp. So this is the way the amp meter works. So if I was to take these meters apart, you would see these current shunts, which is basically nothing but a piece of wire. How much resistance would that be? 50 millivolts or 50 amps? Way down in the milliohms, right? You understand that? So this is the current shunt. So when I put it on ohms, what your meter does, it turns into a voltage or a current source. And then it measures how much voltage is required to cause a certain amount of current flow. And then it translates that voltage over to a resistance, which is pretty neat. So I'll get my meter and take that across and let you look at the shunt there. So it says place, make sure you take AC or DC. If management range meter, make sure you select the proper range. If it's an auto range meter, you need to make sure that the wire's in the right shunt, right? So if you put it across the 100 milliamp or across the milliamp shunt, and then you put 10 amps through it, it's going to blow a fuse. Huh? Yeah. Well, these meters, and you can see on the cat meters, we'll when we do the NC3, we'll probably take one of the meters across. But what they've done on your new meters is your fuses are isolated from each other. They are actually isolated from each other. If you look at the stereo, now remember this is an old meter. The fuse is right out there. My fluke, you got a little plate you can pull off and see the fuse. The fuse is actually down with the battery. So this is the evolution of meters over time where they isolate those fuses. So if one does blow, it's not going to affect the other. We okay on current, guys? So this is current. Resistance measuring, we always measure resistance with power off. But you could damage your meter. Literally, you could damage your meter because it's a source. If you push current back to a voltage, you create a lot of power, right? So remove power from the circuit. Place the meter across what you want to measure. If you measure it good, you take it granted that it's good. If you measure it bad, you isolate that thing, isolate that component because there might be something in parallel with it. And so this is an auto ranging meter, which is good, but some of them's kind of weird. This one right here I don't like. What I don't like about this one is I'm going to put it on volts, so it don't have an AC scale. I'm going to turn it on, and I'm going to put it on volts. And see, automatically it came up to what? AC. And then you got a push button, you got to come over here, you got to press to switch it over. And now I'm going to turn it off and turn it back on. This time it came up to DC. So whatever you measured last on this meter, that's what it comes up to. So right now, if I put this into an AC circuit, it's going to measure what? It's going to measure 0. We can do that on an outlet. So we got to be real careful on that. That's why I don't like this meter. On this meter, you have AC and DC ranges. I like meters that have AC and DC ranges, and that way you don't have to walk. You don't have to flip a switch. So over here on my current, so my current is AC and DC too. So I've got to remember to do what? Switch it between the two. We got a clamp on meter back there that automatically switches for you. I don't like that either. Well, it automatically switches between AC and DC. Where's the one I got open at? This is a auto ranging meter. This is the Craftsman. This would be what we call this an analog meter. This is one, if you got an analog meter, you can still buy them. These are really popular in communication. Communication, when we start playing with these, we call them tune circuits. It's real hard to calibrate a tune circuit with a digital meter because it's constant changing. You got to be real cognitive on the polarity of what you put that into. It's on DC, right? Because you can damage that port or pointer. Clamp on ammeter, we already talked about that. These guys are not actually doing what? Measuring current, they're measuring the strength of the field, magnetic field. So you see why they're called clamp on meters, because you have the two columns that are easy. And you push on the side, it opens the column. You put it across a single conductor. You don't usually put it across two, not unless you want to see if you got if you got one of your phases that are not pulling the right current. So if everything's equal, and then you put this across two wires, your meter's going to show zero. Because every time the current goes out and you come back on a return, it's going to cancel each other out. If you put it across a three-phase, it's going to give you the vectored sum of the current, which is not. If you put it across all three of them, then if they're all pulling the same current, it should measure zero. And that's one of the things you use. So we use these a lot on motors, residential wiring, commercial wiring. What's really nice about these guys is that you don't have to break the circuit. The biggest problem we have is the scales that are available to you. So this is a clamp on ammeter, by the way, even though it don't have a frame. So this is what it is, an auto ranging meter. This is a Cat 3, Cat 4 meter. So normally clamp on ammeters are very thin. They're usually like to be handheld. And also they have the ability, so most clamp on ammeters give you the ability so you can come in and put your common up in here. And then what you can do is you can use the meter for one of your leads, and then you can use this. But this guy here measures volts, it measures amps, and it measures ohms. The amp scale that don't tell me. But what this does, notice there's no DC or AC. So what this does, if you put it on volts and the meter detects AC, it'll switch it to AC. If you put it on volts and it detects DC, it automatically switches to DC. Which is pretty good, because I don't know exactly what it would do if we put it in a circuit that had both AC and DC in it. It would be interesting to see what it did. What do you mean?
Never know what's going to happen.
But this is still a compound ammeter, so what you do is you put it in here. I mean, it don't tell me the ranges, we'd have to look it up. But this is Cat 4, Cat 3 up to 1,000 volts, Cat 4 at 600. So normally they'll double rate the meters, but they'll drop back one for the higher Cat rating. So this is 600 volts Cat 4, 1,000 volts Cat 3. But if you looked at that chart, you'd see that they would be offset by one. Yeah. So but they drop down to the next lower voltage to double rate them. So even though the meter might measure 1,000 volts, if I use it into a Cat 4 source, then I'm on the maximum I should make this thing measure would be 600 volts. Even though the meter itself will measure 1,000 volts. Does that make sense? So it's very, very important to know what you put your meter in. There's clamp-on amp meters. This is a clamp-on. This is a analog clamp-on amp meter. And what's nice about this is we just can put those clamps across an AC circuit. Most of them rated at like 40 amps and 400 amps. So if you're going to measure milliamps, you can't do it with a clamp-on amp meter because it takes a lot of magnetic energy to work those things. I need to look up the specs on these. We got the books. This is a Fluke. It wouldn't surprise me if this didn't have a Hall effect in it where it could actually measure DC current, but I'm not sure what it would. It says complete assignment 3. What is assignment 3?
Assignment 2. Oh, yeah. All right.
Is that in this class?
No, that's the class.
There's like 3 different ones. One fiber optic, one for copper conductor.
Yeah, we have different safety rules for fiber than we have on the.
Which are you?
I can't bring that up without bringing the grade book up. So I can't. I'm not going to bring the grade book up. I'm just looking at the assignment.
Oh.
Oh, email.
No, assignment 3 shouldn't be that. There's a inside course content. So I need to change that last line. And then we should have a section on topic quizzes. And then copper, which is basically what we're in because we're talking about electricity. And then basic electricity 1 and 2. Yeah, so this should be what that should say out there. Complete the basic electricity topic quizzes. So I'm going to change that slide. So the slide is changed. So we have 2. And you can see, if you do them at home, by the way, you can. There's several sources, but you do have access to the PowerPoint, especially if you got 2 smart devices where you can look at it at the same time, which is edit test. Y'all don't have access to this, but to edit test. So somebody took it.
I think it was me.
Yeah, so this basically deals with
That's you?
so this deals with what we just
I'm giving my pass.
yeah. Oh, here where they just got somebody. Auburn got in trouble again. They had he was a tutor or something that took a test for a football player. But he wasn't in this year. It wasn't this stuff. So let's look and see what basic electricity 2 is.
The Microsoft Office class,
Micro, yeah. What, you want the project? Or the PowerPoint? Oh,
I was taking a chemistry class in college, and a bunch of students wanted to go out for pizza. Yeah, I told you that story. And it's a study, and what they want to do is copy my lab work. And that was the last time I had anything to do with it. So yeah, all this was covered in the first thing. So how long do y'all have to do that?
That's right.
No, you have a week from today. So that'd be
First one or both?
both of them.
Okay.
You do that one?
No, nobody's done this one because what it does, if somebody's taking the quiz, it'll pop up something up there saying if you change anything, we'll have to regrade everything. So it tells me when I pop this up how many people's taken this quiz and only one has. But it don't tell me who.
No, I know.
Yeah, he's already spilled beans, right? So what I need to do on that is change that to say basic electricity topic quiz. But y'all know about it right now. I'll just make sure I do that for next class. And I saw that, but I never did go and check what the assignment was. So anytime we finish a topic up in class, then we got a topic quiz up there that you go take. You go up there and take that topic quizzes, and you have 7 days from when we get over this. But even if I give you those 7 days, I highly recommend that if we finish up a topic before the test, then you need to go out and do those quizzes. You can take the quizzes how many times? Twice.
What was that C chat?
Yeah, what we used to do is we did have books for the class, and they're little thin little things, and those books were over $100 a piece. Little thin little books, and we had two. We had one for fiber and we had one for copper. And then basically we realized that the PowerPoints are so in depth that y'all could use the PowerPoints for the book and save y'all $300 on book. And the problem is, this would probably be the last time you'd ever use the books anywhere, because most of this information is available on the internet. Yeah, and then the PowerPoints do a good job of explaining that stuff.
PowerPoints are already easily accessible, so there's no point going on the internet. You may not know what the internet information will be now.
Well, most of the stuff like the pictures and stuff like that. So a lot of information in the PowerPoints come right off the internet.
.edu or .net.
Yeah, I use
But even Wikipedia is coming.
things that this should be called. This is actually the first lecture in